In this presentation, what I am going to do is we're going to compute the characteristic polynomial of this equation. Now we're going to use this to compute eigenvalues and eigenvectors and so on, but specifically what I'm interested in is right now, for this instant, I'm interested in this thing called the characteristic polynomial, also known as the characteristic equation. Okay, so that's the first thing, that's the sort of a building block on our way to developing computing eigenvalues and eigenvectors. Okay, the characteristic polynomial, also known as the characteristic equation. So the characteristic equation or characteristic polynomial, I'll use both names interchangeably. Essentially what we have to do is compute the solution to this. Now this will actually work out as a polynomial expressed in terms of lambda. Now lambda, the solutions to lambda are the eigenvectors which we solve. But for the time being, it's just an expression. Now, in some books you get it as a minus lambda I, and in other books you get it as a or lambda I minus a. Get the determinant of that. It actually doesn't matter. They're both right. So it doesn't matter which way you do. Whatever way sort of looks easiest when you're trying to do it out in pen and paper calculations, just pick whichever one suits you. Now the idea of a characteristic polynomial is you solve for the values of lambda. So if A here is a 3 by 3 matrix, okay, so we should have 3 possible solutions. Okay, they may not necessarily be unique, and in fact in this example they're not unique, but there's usually 3 solutions. There may not necessarily be 3 unique solutions, but 3 solutions. If there were, for n by n case, the n by n case, there would be in terms of the size of A, the dimensions of A, there would be n solutions for lambda. Okay, now lambda again is related to the eigenvectors and eigenvalues, but we're not going to sort of worry about that just yet. We're going to just concentrate on the characteristic polynomial. So let's have a look at this here. Part of our characteristic polynomial is this expression here, lambda times I, and the lambda times I is the identity matrix. So for the time being, what we're going to do is treat lambda as a single scalar. Okay, so lambda times the identity matrix, essentially what you would end up with is something like this. Okay, lambdas are on the diagonal, zeros elsewhere. Okay, so moving along, using our example that we have already, I'm going to use it, express it in the form determinant of lambda I minus a. Now essentially what I'm going to do here is actually what we're going to get is the determinant of this expression here. So first off, where the bar there is, the bars on either side are for the notation for determinants. Okay, so essentially what I'm going to do is just simplify this equation again. Lambda I minus a, essentially just to have a nice easy looking answer. Essentially what we've got to do is this. I'll write a few workings here, but the first one is lambda minus 0, 0 minus 0, and 0 minus minus 2. It's the top row for each. That works out to be lambda, 0, and plus 2. Okay. Next line is, let's work it out a little bit more. 0 minus 1. Okay. This here and this here. Lambda minus 2. Let's get rid of that first. So lambda minus 2 and 0 minus 1, and there we have it again. Minus 1, lambda minus 2, and minus 1. Now I'm just going to sort of write out that the last one is minus 1, 0, and lambda minus 3. That's the bottom row. Okay, so what I'm going to do, I'm just going to the workings will start to clutter things up now, so I'm just going to get rid of them. And what we're going to do now is get the determinant of that matrix there. Okay, so essentially what you try to do is pick a row or column, and essentially it's the determinant of this matrix. Okay, so what I'm going to do here now is pick a row or column. I'm going to pick this. No, I won't. I'll actually just pick the top row. Just keep it nice and simple. I'm going to pick this column here, row here, okay, and what we'll do is get the determinant of based on that, okay. Now, if you're not familiar with how to find the determinant of a 3 by 3 matrix, I suggest you check up on that first, because I'm not going to sort of explain that step at all. I'm just going to sort of state that it's lambda times the determinant of its submatrix, okay, which is what you get when you subtract the first row and first column where lambda is, and we have that expression there, minus 0, well, that goes to 0 automatically, but that's for the, because it's this second element here, and then plus 2 times the submatrix for that last element there, minus 1, lambda minus 2, minus 1, and 0. Okay, I was just checking my workings in my head. So working this out, what we get is lambda times lambda minus 2 times lambda minus 3. The next bit is minus 0 times minus 1, which is just 0. So I'm going to sort of skip the rest of it. Okay. Essentially what I'm sort of saying is the rest of that determinant of that submatrix just works out to be 0, so I'm just going to skip past that. I'm just very conscious of time and space for this particular video. Plus 2 times minus 1 times 0 is just 0. So minus 1 times lambda minus 2. Okay. Now, you might sort of spot that we might be able to come up with a way that we can sort of quickly identify a factorization. That you might sort of spot, well, for both sides we might be able to factor out lambda minus 2, which helps us solve it. But we're not going to do that, unfortunately. I'm going to sort of keep things awkward. Do you know what I will? I will actually just mention that bit. We have lambda minus 2 and lambda minus 2. So what I'm going to do is just incorporate that. It just might help speed things up. So what I'm going to do is multiply the lambda and the lambda minus 3 part, and we get lambda squared minus 3 lambda, okay, times lambda minus 2. And on this side we have 2 times, that'll work out there to be plus 1, so plus 2 times lambda minus 2, okay, on this side. So altogether we would have lambda minus 2 times lambda squared minus 3 lambda plus 2. Okay, and that actually means that we should be able to, well actually you might be able to sort of, we can actually factorize that really quickly. And actually you probably will, so I'll just actually do that. I don't actually mean to do that. This is lambda minus 2 times lambda minus 2 times lambda minus 1. That is the characteristic polynomial, the roots for the characteristic polynomial. So the answer actually will work out to be 1, 2, and 2. Now, I'm going to, it doesn't always work out that way that you would be able to spot lambda minus 2 and lambda minus 2. So what I'm going to do is I'm going to sort of just ignore that, unfortunately, and just sort of work on the basis that we cannot identify lambda minus 2, or it doesn't work out so easily. So what I get when I multiply this out is lambda cubed minus 3 lambda squared plus 2 lambda minus 2 lambda squared plus 6 lambda minus 4, okay? And when I add that up all together, what I get is, I just made a bit of extra space there, just to sort of, when I simplify that, essentially what I get is lambda cubed minus 5 lambda squared plus 8 lambda minus 4. Now, specifically, that is specifically what we were asked for. That is the polynomial, the characteristic polynomial that we require. And look, unfortunately, we got lucky in this case that very obvious. The way we calculated it out, it became very clear that lambda minus 2 was a root or a sort of a factor, and that we could sort of break it down very quickly. But you will not get that in a lot of occasions. Anyway, to cut a long story short, this is our characteristic polynomial. And in the next video, what I'm going to do is talk about how we will be able to solve them without having to multiply through or having to divide through very awkward calculations. So I'm going to stop it there and then start up my next video shortly.